Chapter 3, Section 3.1, it's on graphing lines of the form y equals mx plus b. So what we want to do first is show that the equation y equals x plus 3 is a true statement when 2 is substituted for x and 5 is substituted for y. There are two variables in this equation, so to verify that something is true, we must be given both a value for x and a value for y. So when x is 2 and y is 5, we'll have 5 equals 2 plus 3, and yes, we can verify that that is true. All right. Definition: we say that an ordered pair A, B is a solution of an equation if the equation becomes true when A is substituted for x and B is substituted for y. So the ordered pair 2, 5 is a solution to the equation y equals x plus 3. The solution set of an equation is a set of all solutions of the equation. In example 2, we're going to decide whether the ordered pair is a solution or not. So remembering that the ordered pair gives us a set of x and y values. So the x value it's giving us is 2, and the y value it's giving us is negative 2. So we're going to plug these in. It'll be 5 times the x value, 2, minus 2 times the y value, negative 2. And we're going to check whether or not this is equal to 6. 5 times 2 is 10. These are two negatives, which are going to give us a positive, plus 4, equals 6. So this is false. So the ordered pair 2, negative 2 is not a solution to this equation. In part B, we want to check the ordered pair 0, negative 1/2. 0 is the x value. Plug that in for x. Equals 1 minus 2 times y. Negative 1/2 is the y value. Let's check to see if this is true. Is 0 equal to 1? Two negatives right here are going to make that into an addition. And 2 times 1/2 is 1, since 2 goes into 2 once. And 1 times 1 is 1. This one is also false and not a solution. If we assume for a second that this was a positive value, and a positive value, then the negative times the positive would have given us a negative value, and it would have been true. So we can conclude that the ordered pair 0, positive 1/2 is a solution. Let's check out the next example. We want to find 5 solutions of y equals 2x minus 3, then plot them on the same graph. When I'm trying to find a bunch of solutions to an equation, it's often useful to make a table. So I'm going to make a table of x and y values. Now, because it's impossible to just choose a pair of x and y values that are automatically going to work, what we're going to do is start by choosing an x value and finding the y value that would work. So pick any x value you like. For example, 1 is a good x value to start with. Now if I pick 1, in order to make this true, this would be 2 times 1 minus 3. 2 times 1 is 2, minus 3 is negative 1, so negative 1 would be the corresponding y value. There we go. Now pick a couple more x values. Let's pick a few positive values like 2 and 3, and a few negative values like negative 1 and negative 2. Plugging 2 into the equation gives us 2 times 2 is 4, minus 3 is 1. So the ordered pair 2, 1 would be true. If I plug 3 in for x, 2 times 3 is 6, minus 3 is 3. So a 3 value for y would make this equation true. If I plug a negative 1 in for x, negative 1 times 2 is negative 2, minus 3 is negative 5. And if I plug a negative 2 in, negative 2 times negative 2 is negative 4, minus 3 is negative 7. Now we were only asked to find 5 solutions, but we could just keep plugging in different x values and find infinitely many different solutions. Okay, now we want to plot these solutions. 1, negative 1, 2, 1, 3, 3, negative 1, negative 5, and negative 2, negative 7. The next question is, do the 5 points lie on a line? So I don't want to know if there are approximately on a line. I want to know if they would be exactly on a line. So we're going to need a ruler to be able to tell. I'm going to try to draw a straight line with my line tool. So if I use my line tool, I can see that I can get a straight line exactly through all the dots. To make this a true line, it needs to continue on, so I'm going to draw this past the dots through to the end of the graph. So these 5 solutions that we drew were not enough to represent all of the possible solutions. Once I connect them into this line is the solution, the set that represents all solutions to the graph. So you can see on it further points that are going to be solutions to the graph. If you were to plug in values for x such as 4, you would see that 2 times 4 is 8, minus 3 is 5. That matches up, 4, 5. If you were to pick any point on this line, even a point like this one, now I have to guess to figure out what this is, but if I try plugging in something like 3.2, I would, when I plug it in, get something out that would be very close to a value of about 3.4. So let's select another point in the line and show that the ordered pair satisfies. One of the ordered pairs that we can see in the line is 5, 7. Let's go ahead and verify that. If 5, 7 looks to be an ordered pair on the line, then it must be true for the equation. If we plug 7 in for y, I'm going to get 2 times 5 minus 3 is equal to 7. So if I check this, let's see, we've got 10 minus 3 equals 7. This is true. Any point on the line will be a solution to the equation. Any point that's not on the line will not be a solution to the equation. So let's find one of those and show this. A point not on the line might be anything like this one, negative 4, 2. It's definitely nowhere near that line. It's not going to be a solution. Let's check it. Negative 4, 2. When we plug these values in for x and y, we get that 2 is equal to 2 times negative 4 minus 3, or 2 equals negative 8 minus 3. On the right-hand side, negative 8 minus 3 is negative 11, so this is definitely false. A point that does not lie in the line will not be true with the equation. We call the line that we sketched the graph of the equation. Every point on the graph of the equation represents a solution. Every point not on the line represents an ordered pair that is not a solution. Any equation of the form y equals mx plus b will have a line as its graph. So I can write a few examples of graphs who are lines, simply by choosing the values of m and b. Y equals 7x minus 2, or y equals negative 3/4 x plus a half. If you choose any value for m or for b and write it in this form, y equals mx plus b, you're guaranteed that kind of equation will have a graph that is a line. So there are a few lines we'd like to graph in the next example. To graph these, we're going to begin by making a table of values. It's most convenient to choose the x values we would like and solve for the y values. Let's pick a few values that are negative and a few values that are positive. How about negative 4, negative 1, 0, 2, and 3. I could have been boring and gone from negative 2, negative 1, 0, 1, and 2. I'm just kind of trying to spread these out a bit and pick some interesting values, some positive and some negative. I'll go more standard on part B. For negative 4 as an x value, negative 4 times negative 2 will give me a positive 8. Positive 8 plus 4 is 12. Negative 1 times 2 is positive 2, plus 4 is 6. 0 times negative 2 is 0, plus 4 is 4. And negative 2 times 2 is negative 4, plus 4 is 0. And 3 times negative 2 is negative 6, plus 4 is negative 2. Let's go ahead and graph these. Negative 4, 12. See, I was trying to choose an interesting value and I've chosen one that was just too big. Sometimes it's not smart to choose the most interesting values. We want to choose the ones that are going to be close to home so that we can get something that's going to fit on the graph. We like to choose small values that are going to be centered around the origin to ensure that we'll be able to fit on the graph. -1, 6, 0, 4, 2, 0, and 3, -2. Again, these should be lying exactly on a line. This is an exact linear relationship, not an approximate one, so I should be able to connect them with my line exactly. Looks pretty good. Now let's make sure that our line extends in both directions until it reaches the edge of the graph. An incomplete line would not be considered a full graph. My line needs to go off the graph in both directions to be considered a complete graph. Part B, let's choose some more traditional values for x and y. We choose our x values, then we solve for the y values. Now, in this one, I'm not going to choose -1, -2, 0, 1, and 2 because of the fraction. Because of the fraction here, I want to choose smart values, values that are going to multiply by 2/3 and give me a whole number. So, because the denominator is 3, I want to choose only values that 3 goes into. So if I want 2 negative values, I better pick -6 and -3. And 2 positive values, I better pick 3 and 6. Let's plug these in. 2/3 times -6 is -4, plus 1 is -3. 2/3 times -3 is -2, plus 1 is -1. 2/3 times 0 is 0, plus 1 is 1. 2/3 times 3 is 2, plus 1 is 3. And 2/3 times 6 is 4, plus 1 is 5. Let's graph these values. -6, -3, -6, -3, -3, -1, 0, 1, 3, 3, and 6, 5. Again, these appear to be on a straight line, so let's connect them. And using your ruler, make sure that your line goes through in both directions to be a complete solution. Alright, now I want to talk about the y-intercepts of these graphs. The y-intercept of the first graph is 0, 4. The y-intercept of the second graph is 0, 1. Notice that I had chosen 0 as one of my points in both cases, so the y-intercept is showing up whenever I choose a value of 0 for x. Also notice that this value that I get for the y-intercept is part of the equation, because when you multiply 0 times anything, you're going to get 0. 0 times 2 is 0, plus 4 leaves you 4. 0 times 2/3 is 0, plus 1 leaves you 1. So the y-intercept is going to show up in the equation. So no matter what m is, the y-intercept of the equation is always the ordered pair 0, b. When you plug in 0 for x, 0 times m is 0, plus b is b. So without graphing, I can state the y-intercept of each of these equations. The y-intercept of the first one is 0, -5. If you plug in 0 for x, you get -5. And if you plug in 0 for x, you get 0. There are 4 ways to describe the solutions to an equation. This is known as the rule of 4. You can describe the solutions using an equation, a table, a graph, or using words. So let's look at the first example here and describe the solutions using a table. So once again, we're going to choose any x value and find the corresponding y values. So here I'm going to use a standard -2 to 2 system to get 5 values. We plug in -2 for x. -2 times 4 is -8, minus 3 is -11. If I plug in -1, I'm going to get -4, minus 3 is -7. If I plug in 0, I'll get my y-intercept, which I know is -3. If I plug in 1, 1 times 4 is 4, minus 3 is 1. And 2 times 4 is 8, minus 3 is 5. So my table lists just a few solutions, gives us one way of describing the equation. Let's describe the same equation using a graph. So I'm going to start by graphing the 5 points that we've just found. -2, -11 is about here. 1, -7. 0, -3. 1, 1. And 2, 5. Let's go ahead and connect these with a line that goes right through the center of every point and crosses through both ends of the graph. The graph gives us a little bit better of a picture than the table can because it includes all the points in between the ones we chose. Alright, let's consider the graph shown right here and create a table based off of the graph. As a hint, there are 2 ordered pairs already circled. You can see those right here, but there are some other ones that we're going to be able to find ourselves. Let's go ahead and circle first all of the ordered pairs. So we have one of them, another one over here. A true ordered pair is going to cross right through the corner of a box. So we can see one appearing over here. This one's close, but it's not quite at the corner. This one's also close, but not quite. It needs to go right through the corner of a box. Let's look for another one, probably the one at the end right here. And I don't see any until I get to the end right here. So the ordered pairs that appear have x values and y values of -10, 6, -5, 3, 0, 0, 5, -3, and 10, 6. And that's the end of this section on graphing the equations of lines.